started. In our last lecture, we covered a number of algorithms that we could use to analyze large data sets of face images, right? And obviously, the first one that we saw was linear least squares, meaning PCA, principal component analysis, and that is famously known as eigenfaces, because the eigenvectors that you get from the PCA analysis of images of faces represent faces. So eigen from the eigenvectors and faces, eigenfaces. An extension of that is to use the Laplacianfaces, which is just one additional or one extra term that we can add into that equation, right? And for this, we're going to use the metric that we have used many times already here in this course. So we're going to define the metric Sij equal to the exponential function of xi minus xj, maybe the true norm. We're going to use the true norm here divided by the variance, right? So that's an exponential function that we have been using a lot in this course. And we're going to do that if the vectors xi and xj are the Euclidean distance, right, is smaller than some threshold, some small value, let's say epsilon, for epsilon larger than 0 but small, okay? And 0 otherwise. And that means that in our space, feature space, P, remember the number of pixels in my image, two images of two different faces are going to be assigned a similarity measure according to this equation if their Euclidean distance is smaller than the threshold, and they're going to be assigned a similarity of 0 if that distance is larger than the threshold epsilon, right? Okay. And now this exponential function obviously looks something like this, which means that the closer the two vectors or the two face images are, the more similar they are considered, exponentially so, right? Make sense? Okay. So obviously here, this is, I'm using the same notation I used last time, right? These are the simple images of our faces, right? And let's see if that works better. And sigma, as I said, it's a variance, right, of that exponential function. Now, assuming that our metric, like in that case, is symmetric, right, because I'm going to assume that Sij is equal to Sji, right? So it doesn't matter if I interchange them. Then that means that my similarity matrix, right, where the xi's are in my rows and the xj's my columns, then that matrix is going to be symmetric, right? Symmetric matrix. And it's obviously positive semi-definite. Okay. Now, so that's what we have. Now we wish to find a new space that where the vectors xi correspond to yi and xj to yj, and I want a space where that distance multiplied by my Sij's, which are the weights of these distances that I have computed here, right, on this left-hand side, that this is as small as possible. So I'm going to sum over this for every ij pair, right? So this is the summing term of ij, and I want to minimize this. Okay. Now to do that, we note that we can write this as 1/2 the sum of every ij pair of W transpose xi minus W transpose xj square Sij, right? Because this thing is yi, and this thing here is yj, right? So I'm just finding a projection matrix, or vector rather, that allows me to project from my x representation to my y representation, as we've always done, right? So that's what I'm interested in. I just added this 1/2 because it's mathematically convenient for me to then cancel out with the derivatives, right? So, but that's just a mathematical convenience. So I can rewrite this now as the sum of my ij pairs of W transpose xi, Sij, xi transpose W, right? And all I'm doing here is I'm taking the square of that, right? Minus the sum of every ij pair of W transpose xi, Sij, xjw. And I can rewrite this as the sum of W transpose xi, dii xi W minus W transpose capital X, capital S, capital X transpose W, where here capital X is a matrix whose columns are my xi's, so x1 through, say, xn. And S, it's a matrix whose entries are Sij's, right? For the ith, jth rows and column. Right? Oh, and D, sorry, I forgot D that I have here. And D is a diagonal matrix with the corresponding D1 through D11 through Dn. And dii is equal to the sum over all j's of Sij. Right? Okay. So now with this new notation, I can write this equation, the very top equation here, as W transpose. Now this is capital X, capital D, capital X. So this is going to be X D X transpose W, right? Minus, what do I have here? W transpose X, capital S, X transpose W. And obviously, I can just write this as W transpose X, D minus S, X transpose W, right? Yep. Everyone? And now here, where my matrix L, I'm going to call this L. So where L, it's equal to D minus S. And this matrix, if you've taken my machine learning class, you'll notice this matrix is called the Laplacian matrix, right? So this is the Laplacian matrix, and that's why we call this Laplacianfaces, because now we're going to do an eigenvalue decomposition of this, right? So our goal, remember, was to minimize this, which is the same as minimizing this, right? Which means that I want to find the argument that minimizes this projection W transpose X LX transpose W, subject to some scalar, right? Remember, it's an eigenvalue decomposition, so I have to fix a scalar. And I'm going to fix a scalar that W transpose X d X transpose W is equal to 1. And then that means that this can be solved with a simple eigenvalue decomposition, a generalized eigenvalue decomposition. XL X transpose W equals lambda capital X d capital X transpose W, right? And that's our solution. And obviously, these are the eigenvectors and eigenvalues, right? The eigenvector here, W, and lambda, the eigenvalue, right? And we are looking for the eigenvector that's associated to the smallest eigenvalue. This is our least square solution. Okay? You see this? So it's just another way of defining the subspace that describe faces in my RP space, right? So this is going to give me, right? So instead of just taking one eigenvector and one eigenvalue, I take the first R eigenvectors as usually to the R smallest eigenvalues. I'm going to find the subspace like I did with PCA that defines the subspace of all the images of faces in RP. See that? Yeah? Okay, any questions? So the only difference between eigenfaces or using PCA and this is that here we use a different metric, right? And the metric is defined by an exponential function like this, right? And that now I am redefining that equation here according to the metric S, right? Which I have here defined in this equation, right? S, right? Okay. Now, obviously, you can test a variety of metrics. There's no constraint for you to use that specific one, right? This is just a very common one that we typically use in computer vision. All right, if there are no questions, let's move on to, yes?
About the first equation, how to compute the variance, that variance?
Oh, this is whatever variance you want. This is a parameter that you have to set, and that variance determines that width, right? Well, more than the width, because that is also given by the epsilon, obviously, depending how. But so if you have a small variance, right, this width is going to be narrower. So you're going to get a metric that looks, okay, that doesn't work. That looks something like this, right? So if the variance is small, it's going to look something like this, right? And if the variance is very large, it's going to look something like this, right? So that's how you determine whether you're giving more relevance to the images that are very, very, very similar to each other, and much less relevant, exponentially so, very fast, as the images are more divergent, versus this one that up to a certain point, up to that point of the variance, sigma, you consider them almost equally good, right? Any other questions about this? All right, so the next algorithm actually is another extension of PCA, like this one, and you'll see this. I mean, obviously, it's obvious that there's so many extensions of PCA because PCA is a least square solution, and what we engineers really know what to do is to solve with linear least squares, right? Linearize our equations if we have to, but we really like linear least squares. This one is called linear discriminant analysis. And people just commonly know it or refer it to as the LDA algorithm. And LDA is nothing else than the least squares extension of PCA, but where we consider the classes of the samples, the Turing samples, right? So in PCA, our Turing sample math cal x, it's equal to xi, I from 1 through n, right? So the n images that we have. That's it. That's all we need, right? Now, if I want to do detection of faces, we saw how we could do that with eigenfaces, right? If we want to do recognition of identity, then I have a projection of a new test vector t. I project it into the PCA space, and I find the closest vector xi to that, and then I assign the class of that xi to that t, right? If I have more than one xi per class, I can find the Gaussian distribution in PCA space that defines that class, then I use the Mohnovich distance that we introduced, and so on, right? You can have all these different variations. Here in LDA, you do that from the get-go, right? So what you want to find is a projection, like what we did now, that we go from xi's to yi's, where yi's are my values in the projected space. But in that case, I want to find a projection that is, I want to find a projection that maps samples, meaning sample images of faces, samples of images of the same individual or the same class very close to each other in my projected space, and sample images that belong to different individuals as far away as possible from each other, right? That's my metric. That's all I care about, right? Okay, so let's see how we can do that. So I have my xi samples. I have my xi samples as always, and so for example, okay, none is working, huh? All right, that works. My xi samples from the ith class now, that would be, right? So this is for the ith class. Now, I generally say class because typically in face recognition, that would be individuals, right? Me versus you versus someone else. But later on, we'll see that that can be applied to anything else. It could be the facial expression, it could be the gender, it could be the age, it could be anything, right, that we're interested in. Any property that we want to model. So I have xi1 through xini, right? So these are my ni samples for each of the class. And note that I write ni because the number of samples per class may actually be different, right? From class 1 to class 2 and so on. And then we can compute mu I, which is the mean vector of this class. So that would be 1 over ni of all the xij's, right? The sum of all the xij's. Okay. So as I said, we're going to define now two metrics, and I'm going to define two possible metrics. But as always, you can define your own metric, right? I mean, you're not bound to these two metrics. I have to find two metrics that measures how close samples are, samples of the same class are to each other in the projected space, and how far away vectors of different classes are. Okay. So let's see. So the first metric, LDA typically has used what's called the within class scatter matrix. And this is defined as SW, which is equal to 1 over C, the sum of let me write this like this. The sum of all j of xij minus, oh, I'm sorry, my bad, of the sigma of sigma, why don't I write, yeah, sigma I, that's fine. I think notation is better. So this is the sum, this is sigma, very confused, where sigma I is equal to 1 over ni, the sum over all I of xij minus mu mu I times xij minus mu I transpose. Right? So as you see, this is nothing else than the covariance matrix of the simples in the same class. Right? And this is the average covariance matrix. That's it. Right? And then the other metric is the between class scatter matrix. And this is called SB. And this is 1 over C, the sum for over all I from 1 to C of mu I minus mu times mu I minus mu transpose, where mu, it's the mean of all the means, right? So you could write mu here as 1 over C, the sum of mu i's, right? So far, so good? Yeah, question. C, it's a number of classes. So I goes from 1 through C. That means the number of classes that I have here. C, the number of classes. For example, the number of identities. All right. So now, as you see, the within class measures, right? It's a metric that measures the closeness of each simple in class I to its mean, right? To the mean of class I, right? You see that? Whereas the between class measures the distance of every class mean to the global mean. So I want to minimize this, and I want to maximize this, right? So what I need is to find the argument that minimizes, actually that maximizes. I mean, you can write it the other way around. That maximizes V transpose SB. V, actually, let me make it capital V, because I'm going to take more than one solution, eigenvector, and SWV, right? If you want to minimize, then you just invert this, right? SW over SB, okay? So again, SB is just a matrix that defines the metric that you want to maximize, and SW, a metric that you want to minimize, right? But it doesn't matter how you define these metrics, as long as you define them in a way that measure class similarity and class dissimilarity. All right, and this obviously, it's the same problem that we had before. So the solution, as always, is given by a generalized eigenvalue decomposition problem, right? So I have SB, capital V, SW, V sigma, capital sigma, where capital V is a matrix whose columns, V1, V2, V3, and so on, are the eigenvectors of this generalized eigenvalue decomposition problem. And capital lambda, it's a diagonal matrix with lambda 1, lambda 2, lambda 3, and so on, the eigenvalues, right? The corresponding eigenvalues. So you want to keep as in PCA and Laplacian phases, the first R eigenvectors associated to the R largest eigenvalues. And that's your solution, right? So this is our solution. Now note, obviously, that I can compute this as SW inverse V lambda, right? And I can just solve with an eigenvalue decomposition equation. Now, the only reason I may not be able to do that is because, okay, anyone can tell me why I may not be able to do that? Come on, there's a classical question for a final exam. Why may I not be able to do that, right? Because you have to know these things. Because as I said, computer vision is nothing else than knowing all these tools that we're describing throughout, and then putting this tool A here, this tool B here, this tool 3 here, and building an algorithm that way, right? That's computer vision, really. But if you start doing that and say, oh, I know, I'm going to do Ix of SW inverse, it's not going to work, and you're not going to know why it's not working, but you have to know why, right? Why is it not going to work in general? In some cases, you may get lucky and it works, but in general, it's not going to work. Why?
SW isn't invertible.
What's that?
If SW is not invertible.
And why may it not be invertible? It is. It is. It's a square, but it's non-invertible generally. It's a singular matrix. Why? Look at the definition. Why that might not be invertible? What does it mean for a matrix to be invertible? What's that? Full rank, exactly right. And what does full rank mean? That and that what? Yes, you're right, but what does this mean? Full rank, what does it mean in RP, in my space RP? What?
I would say, well, I would look at the eigenvalues first of that matrix. If there are any zero eigenvalues.
Right, and that.
Any linearly dependent.
Right, so that would mean that it's rank deficient, right? And what does this mean in RP?
There's really a lower dimensional space.
That there's a null space, right? Exactly right. So that my matrix does not span the original feature space RP, right? That I started with P, the number of pixels, right? But rather, the range of space defined by SW, it's a subspace, right? And what happens in that case, that I cannot invert it, right? And that's generally going to be the case because if I only take faces, or even faces of a specific individual, then that's generally going to span subspace of RP, and therefore it's going to have a null space. Therefore, SW is non-invertible. There is a very easy solution to that, which is you do SB, there we go, times SW plus some, let's call it, I don't want to call it lambda because that's, we're going to be confused by the eigenvalue. Let's call it, I don't know, A. Actually, let's call it epsilon. Epsilon's a good. Epsilon times the identity matrix inverse, right? And then do an eigenvalue decomposition of this. Okay. And that's called a regularizer. You regularize your matrix, SW, or whatever other matrix. We're now here, epsilon is a scalar larger than 0, but very, very small. Okay? Now, what this is going to do, because the identity matrix has ones in the diagonal, then it's full rank by definition. So it spans a whole space. It's actually all the basis vectors that are orthogonal to each other and norm 1, right? So now the matrix is invertible. But if I multiply that matrix by a tiny, tiny scalar epsilon, then I don't have that problem anymore, right? I all of a sudden can solve for the invertible issue without having a huge effect on SW, because the values that I'm adding here are tiny, right? You see that? Okay, good. So that's that's LDA. All right, next one, it's just yet another extension, which is how we're going to extend these algorithms that we've defined here, PCA, Laplacianfaces, LDA, and so on, from vectors. Remember that we're still using a vector representation. That means that we take the original image and we vectorize it, right? By raster scanning the pixels. But how about just taking the image itself as a matrix? And if I have a tensor, right, it could be the matrix and the 3 channels, the RGB color channels, then I have a tensor, right? And then I just want to do the same things, but with a tensor decomposition, then that is called Tensorfaces. So I'm just going to very briefly introduce the basic notation for that, but you have all the details in the paper I posted online for you. Okay. So what we're going to do, we're going to take. Let's see if I can use this. Okay. So we're going to take a data matrix, right? So my data matrix D, which is defined in the real domain of I1 by I2 dimensions, okay? And the decomposition of that is going to be D equals U1 sigma U2 transpose, okay? Where now, so where here, where U1 is in the real space of I1 by, excuse me, this is, oh yeah, I1 by J1. And sigma is a diagonal matrix, obviously. And U2 is R I1 R I2 by J2. Okay. And in tensor notation, we can represent this as D is equal to sigma. This is cross product 1 times U1 cross product 2 U2, where this notation, cross product M, right, is the mode M product which of tensors, which is defined, so the mode M product defined by or as A x M B of I1 I n minus 1 J n I n plus 1 I n capital N. This is going to be equal to the sum of over all my I n's of A I1 Now this is small a, it's the ijth entry of capital A, as always, right? Okay. Comma in minus 1, comma in plus 1, all the way to capital N. That should be. And times b jn in. Okay? This is jn in. Okay? So this is just the product for tensors as we covered briefly in 5460, and you also had this in one of your homeworks early on in the course when I asked you to solve for the gradient descent algorithm with tensors, right? Which uses the same type of notation and solution. And now here, obviously, in this notation, I have my tensor A, which is, I'm still defining in the real domain. So in that case, I'm going to have I1, times I2 times all the way to I capital N, and B, which is J capital N, small n, we've said, right? This is, small n times In. Okay? My two tensors. Okay? And now with this, what this notation allows me to do, this tensor notation, is to decompose our data matrix as follows. So we can decompose D as the product of Z x1. Remember, that's the tensor product, the M mode tensor product, or one mode in that case, times, so U, let's call it U people. This is going to be the matrix that has the information of the identity of the person, right? Okay. And now for mode 2, we're going to multiply this with another tensor that has information about the view, right? The viewing angle of the face, right? And note that I'm putting this in different modes, right? In different modes here. So not to have them overlap with one another, right? So their representation is going to be orthogonal, in different modes, okay? Described in different modes of the tensor, right? x1, x2, up to xn. So this one is going to be cross product 3, so 3 mode times, here I'm going to put, say, the illumination. In mode 4, I'm going to add the expression. And in 5, I'm going to just have some residual mu O, which are going to be my basis vectors, right? And these are the basis vectors I'm most interested in. To represent my faces independent of these other terms. Okay. Now, there is, in the paper, you have more details about this, but in order to get this decomposition, you need to use the M-mode SVD, right? Because unfortunately, can't use regular SVD because that's not for tensors. And in brief, this has a couple components. First, it's a for loop from 1 to capital N, where I first compute this data matrix Z, X1, U1, X2, U2, X3, and so on, up to X capital N, UN. This is capital N, the number of elements that I want to use in my decomposition, and then solve for that Z, which is D times 1 mode 1 all the way to capital N, UN. Right? That's it. Now, to be able to solve SPD using this little trick here, you have to still what's called flatten D tensors, which means that you have to represent the tensor as a matrix, right? And that's the same trick that we did for vector representation, right? So we went from a matrix, an image, to a vector by vectorizing it. We flatten the tensor so that we take the different orders of the tensor, different modes, and we put them next to each other, and we describe everything as a big matrix. And that's what allows us to do this. And you can use this type of representation to solve any of the problems that we have introduced before, right? If you use this SVD, you solve for eigenfaces, only now that you have eigenvectors that define the identities, eigenvectors that define the post variations, eigenvectors that define the illumination variations, and so on, right? So you have all these different representations all in a compact form as a tensor decomposition. But you could extend this to any other metric, similar to Laplacianfaces or similar to linear discriminant analysis, okay? So it's just extensions of everything we've done with tensors, okay? All right, any questions about this? All right, I want to do one more, and then we'll change gears a little bit, okay? The last one I want to talk about is the obvious extension of all this. These are all still linear methods, right? We want to extend this to nonlinear least squares, also called deep learning, right? So in faces, this is usually called Deepfaces, right? Very innovative. So let's see that, okay? Shall we? All right, so I posted one of the original papers, not the very, very first paper, but one of the very first successful papers to use deep neural networks for representing faces using the same approach that we've described here, but in a useful framework. And that was the very first successful algorithm, meaning that it achieved better results than anything else at that time, okay? And that was actually just a few years ago, and now there are other networks that work slightly better. I'm just gonna browse through them at some point, but we're not gonna get into the details because after that, everything it's just details, right? I just add one more layer, I just at one larger data set, training data set, or what have you, but the fundamentals are exactly the same. Okay, so this first one, which paper I posted in Canvas, works as follows. First, you detect a few landmark points in each of the faces, right? So you start with your training set as always, right? With your xi's, I1 through n, right? And now you detect a few landmark points. I think that in that particular paper, they use like 3 or 4 or 5, maybe 6 points, right? And say the corners of the eyes, the corners of the mouth, and the chin, right? It could be as 5 points, for example, and the tip of the nose. And now you align all face images, all training images, using some algorithm, right? Do you know of an algorithm that we could use to do that alignment? Per-Christus analysis, right? Very good. So now align the data. I would say generally one would use per-Christus analysis. Or actually, let me say per-Christus alignment to be more precise. Right? Okay, the least square solution. Now, what we're going to do next, now, of course, note that this is a 2D alignment, right? This is just 2D. I'm just aligning the images themselves. Now, what we're going to do next is to map the shading of these aligned faces to a 3D model of a face. Now the question is, to which 3D model are you going to align it to? So at the time when this paper came along, the 3D models of faces were not very good, or we couldn't recover the 3D model very accurately. So what they did is they took a database, there's databases out there of people that have taken 3D images of faces of people, right? So you have the 3D shape of many people. They compute the 3D per-Christus mean, and then they created the mesh of the 3D per-Christus mean face, right, in 3D. And then they map the shading of every image onto that standard 3D model, okay? Now, these days, when we talk about shape, did I talk about that algorithm that we have now, that from a single 2D image you can recover the 3D shape of the object, right? So the way you do that is by using regression, usually with deep neural networks, right? So your training set is 2D images, the landmarks on 2D images of an object like a face, and your yi's are the z coordinates of these landmark points. Now, if you assume an affine projection matrix, right, and a fine camera, the x and y's don't change. Only the z's change, right? Only the z matters. So that means that you only need to recover z. So again, your training data, xi's, the coordinate points, the landmark points, the xy's, right, or uv's that are equal to the xy's. And now you need a function f of that xy onto zi, right? And now you train that using gradient descent, right, on your training data. Now when you're given a new image of a face, you pass it through that regressor, and it'll give you the three-dimensional shape of that particular face. And that works better, and that's what we use now, because you're not using a generic 3D model like this. You're actually using the specific 3D model of that person, or at least a very good approximation of the 3D shape of that person, right? And that's obviously better, but this is what I meant by details, right? I mean, these things keep improving, so now instead of using a generic model, we use a specific model, but the overall architecture of these methods is still the same, right? Okay. So, after you have this, so maybe I can do that a little bit more. Let's do that just to review, right? So this is just, for example, if you use a generic model, you can find it by defining P as your camera matrix, right? The camera projection matrix P, which means that if I have a 2D image of a face, this is the same as the 3D image projected using my projection camera matrix P, which I can find by minimizing R transpose sigma inverse R, where R is equal to the least square solution, or the least square equation rather, x 2D minus x 3D P, right? So what I'm looking at is I want to find the minimum, right, the projection that minimizes the reconstruction error, right? Remember, this is typically called the least squares criterion or loss, or also the reconstruction loss, because we typically use the 2 norm. This is also many times called the square loss. Okay? Right? And then this is the covariance matrix of the variations over my 3D models, right? So that, remember from active shape models, that we added that covariance matrix because we want to know which are the variations that are most likely to occur, right? And that's what this does here too, right? So again, as you see, the equations that we have seen up to now for structure from motion, for camera models, multi-view geometry, for optical flow that we saw in 5460, for shape models like active shape models or appearance shape models, and for this in deep learning, this one and the same. They're just no big differences, right? We just use the same method over and over and over again. Okay. Now, obviously, this leads to a nonlinear system of equations because of that inverse of sigma, right? But you can linearize this actually very easily. Typically, people will use the Cholesky decomposition to linearize this system of equations and then solve with least squares. Okay. Now, why do I want the 3D model? Well, I want the 3D model usually because I want to what's called frontalize all the faces, meaning that I want all the faces to be frontal looking, right? Because if I have 2 pictures of you and one is looking frontal and the other one is looking 45 degrees from frontal, then this matching, remember they're matching pixel with pixel to pixel, the shading of these pixels is going to be completely different, right? It's going to be meaningless. So I want to align them as well as I can, right? So now I'm going to use this to actually do that alignment. So so now what I'm going to do is I'm going to frontalize the xi's, right? Maybe let me call them xi tildes, I don't know. And then after I have done this, this leads me to, that gives me, this yields my set of frontalized images and the corresponding labels, right? And those labels, if I do recognition of identity, would be 1, 2, 3, 4, 5 natural numbers for each identity, right? So each person is going to have a number. Okay. And now I already have a training set I can use, and now I train a deep neural network with either stochastic gradient descent or batch or mini batch, right? Remember stochastic, I just take one sample at a time and I run gradient descent, just one sample at a time. Batch means that I use all of my training samples at every iteration. Mini batch is a subset of them, right? Now, which neural network are you going to use? There are no prescriptions here. This is trial and error right now. And I'll talk more about this, hopefully, if we have time in our last lecture on what are we working on to try to more formally define how to define these neural networks. But right now, you don't really know. So you're just going to follow the practice that everyone is following because that seems to work, right? And what seems to work, in particular for faces, is to have a first layer, right? So remember that we have a DAG, a directed acyclic graph, and that means that we have a first layer of nodes that have edges connecting to the nodes on the second layer or after, right? And the second layer nodes connect to the third layer and so on, always feed forward, right? So it's a directed acyclic graph. So the first layer is typically a set of convolutions. Okay. For example, as an example, so let me say e.g., we can have F filters, right? F linear filters like the linear filters that we defined in 5460 in our previous class. F filters, right? And let's say of size P by Q by 3, where P and Q are the number of rows and the number of columns, and 3 correspond to the 3 color channels, right? Maybe RGB, right? Red, green, and blue. And usually you're going to define what's called a stride rate. So I don't know if I have this here. What they use in that paper. Okay. But the stride rate, if it says in the paper, it's not in my notes, you will say at how many locations in the image you're going to apply your filter to, right? If you do a stride rate of 1, that means that you go pixel by pixel by pixel, right? So you center the window of the filter at the first pixel, and then you move 1 pixel to the right, and you center the window of the filter there, and then you move 1 pixel to the right until you exhaust all the pixels in the first row. Then you move to the first pixel in the second row, and you continue, right? As if we were reading the vector of that matrix, right? We were vectorizing that matrix. If you do a stride 2, that means that you go every 2 pixels. Stride 3, every 3 pixels, and so on, right? And people do that because, obviously, this is easier said than done. If your filter is P by Q by 3, and you have F of them, maybe you're going to do usually between 20 and 60 different filters. That's a lot of computations, right? And usually these filters are not described as a convolution, but rather as a correlation, which runs a little easier and faster. You don't have to use the fast Fourier transform to transform into the Fourier domain, although that will work pretty well as well. But it's just another way of running this in GPU. But still, it's a lot of computations. So you just want to make it as simple as possible. And that's why you'll usually run some M stride. Okay. Simplification. Now, once you have done this, you're going to add a second layer, which is typically a max pooling layer. And pooling layers are used by layer, again, a row of nodes. That I mean, well, actually, this is going to be a tensor, right? It's not going to be a vector, but it's going to be a tensor because the filters are going to output a set of tensors, right? There are, I don't know, P1 by Q1 by 3, right? And then what you're going to do, you're going to apply a nonlinear function to those outputs to simplify this outputs as much as possible, right? So you're going to take a window in these tensors, and within that window, you're going to compute the maximum value. And that maximum value is your output. That's it, right? That's max pooling. But you could use any other nonlinear function for the values of that window within that tensor, okay? And that's a pooling. This is just meaning that you are pulling from there. You're simplifying the notation as much as possible. Obviously, you could use PCA if you want to, right? I mean, it's up to you, although that would be a linear transformation. Okay, so that just means that you're using the max function, right? So, for example, I think in that paper that I posted in Canvas, they use a 3x3 window with a stride 2. It means that within these windows, I take the maximum, and that's the value I keep. Now, this may be followed by a third layer, which is, again, a convolutional layer. And the fourth layer, which is another max pooling layer. Anyone knows why you'd want to repeat this? If I've already done convolutions and pooling, why do I have another layer that does convolution again and then pooling again? Anyone wants to guess? That's a very good guess. It's true that you might be able to do that, but you could have done this in the first layer to begin with, right? These F filters are filters at different scales, right? So you could add as many scales as you want there. Why not do that? All right, you don't know? You sure? No one knows?
Will the filters be the same?
Hmm?
Will the filters be the same as the first one?
They don't have to be, but they could be the same. They could be exactly the same. So you're in good company if you don't know the answer. No one really knows. But the short answer is because people have tried different things, and this seems to work better. And that's how deep learning works. There are no magic bullets in deep learning. It's a trial and error process, right? You put things together, you try. If first you have to define an architecture that allows that converges, right? That allows you to use gradient descent, stochastic gradient descent or batch gradient descent. But if it doesn't converge, then you can train, right? But even if it converges, does it then work for your testing data set, right? And that seems to work better. So people do it usually twice, sometimes more times, right, networks have been getting deeper and deeper, meaning that you keep adding more and more layers like this. And then people, what they'll define is what's called a module. Say layers 1 and 2 here, it's a module, right? And then they keep repeating this module many times, right? Maybe 3, 4, 5 times. But if I repeat the module 5 times, that's already 10 layers, right? But it's OK. You keep doing that. And generally, if the module is well-defined, like something like this, by well-defined means something that's known to relatively work well, the more modules, the more layers you add, generally, the better your results are going to be. Nobody knows why, but that seems to be the case. Okay. And then at the end, although this has changed, I'll talk more about this at the later lecture, but then at the end, the last 2-3 layers used to be, and in some cases they still are, what's called fully connected layers. Now, fully connected means that if I only had a row vector instead of a tensor of nodes, that every node from the previous layer is connected to every other node in the next layer. Okay? So you have all the possible edges exist. They're directed, forward-looking, and they all exist. So it's typical to have 2-3 layers at the end. They're fully connected. Okay? Now, the max pooling and the convolution layers are not fully connected, right? Because they are applied locally in the tensors. Now, you can also add layers, or in this fully connected, obviously, but also in some other layers here, some other nonlinear function, right? So originally, people used a sigmoidal function that we have already introduced in an earlier lecture, right? I forget, it was maybe lecture 3 or 4, whenever we talked about this, remember? 10H is actually very common in some networks, and one of the most used ones is ReLU, which is rectify. It's a rectified linear function that makes things seemingly work a little better. Okay. Now, in the final layer, in the very final layer, we usually use, typically, not always, but we generally use the softmax. Classical softmax that you learn in statistics. And for example, the C-way softmax, right? If you have C classes, the C-way softmax would be so remember, the softmax is just a statistical function that measures the probability of each output, right? In our case, each output is a class. So the probability of each class, right? So the probability of class C would be equal to the exponential function of the output. Let's call this output here O1 through O capital C, right? So a small c for, small c 1 through C. Then it would be OC divided by the sum over all C's of actually I, because this is going to be confusing. The sum of overall I of the exponential of OI, right? So far, so good. So that's how you define the architecture. And I use that word architecture loosely, right? Because this is the design of how I'm going to put the layers and the connections and which filters I'm going to use and at which scales and which size of the filter, and they're going to be Gaussians, they're going to be what they're going to be defined by, right? So all these terms have to be part of that architecture, and then all these connections that you define, the final network defines a topology of the network, right? And that's a topology of that specific network. All right. Now, once we have done this, we still need to define a way to train this deep neural network, right? And that means that obviously we're going to use gradient descent. I think the paper that I posted in Canvas uses a stochastic gradient descent, but it doesn't matter which one. But you have to define a loss function. Remember, the loss function is the one that you want to minimize or maximize with gradient descent or gradient ascent, right? And the loss function is the one that you're going to differentiate and solve for, right? And then you're going to backpropagate with the backpropagation algorithm that we defined in class, right? All right, so a very typical loss function that was introduced for deep neural networks is the cross entropy loss. So let's talk about this one. Because this function, this loss function, you're going to find it not only in this paper for faces, but in many other papers for object recognition. So it deserves, it is worth spending a few minutes understanding what this loss function is all about and why is it useful and important. Okay. So, okay, I'm out of time, I don't know. Okay, we'll leave it here. I'm going to cover then the cross entropy next time. So I only have to cover the cross entropy. I also want to talk about data sets, and then we'll talk about higher level tasks in face recognition and extensions of these neural networks that have been applied to object recognition to emulate what we have done here. Obviously, you could do object recognition with PCA, with Laplacian maps, with ICA, which is another extension of PCA, right? For PCA measures correlations, linear correlations. ICA measures nonlinear correlations. LDA, kernelized versions of this, which I cover in the machine learning class. And then deep neural networks, right? And I'm just going to jump to deep neural networks because everything else is exactly the same as we have covered here for faces, but for other objects, okay? All right, I'll see you Thursday.